Hello and welcome to another episode of Passages, a scientific podcast presented by Amundsen Science and recorded aboard the research icebreaker Amundsen. My name is Amélie Desmarais. I am a coordinator at Amundsen Science and I will be your host for today's podcast. We are recording this episode while navigating in Lancaster Sound, or we're almost in it now, a major gateway of the Canadian Arctic. Today's rather cloudy with outside temperature of -2 degrees, but over the next few days, temperatures are expected to decrease to about -10 degrees. With this kind of cold for an extended time period, an exceptional phenomenon, though sometimes taken for granted, can take place. Ice starts to form around the ship, and this so-called sea ice is exactly what we are going to talk about today with our guests. We have with us Peter Sutherland, research scientist at IFREMER, l'Institut français de recherche pour l'exploitation de la mer. Hi, Peter.
Hi.
We have Marcel Babin, researcher at the Takuvik International Research Laboratory. Hello, Marcel.
Bonjour.
And finally, Jens N., associate professor at the Center for Earth Observation Science of the University of Manitoba.
Hello.
Glad to have you all on board today. So, many thanks to the three of you for joining me today. It's a real pleasure to have you around the table, and I would like for us to start by introducing ourselves and our role on this cruise. So let's start with you, Marcel, our chief scientist for leg 4 of the 2024 Amundsen expedition. Can you tell us more about your role on board, your research objectives for this campaign?
So the chief scientist during these scientific cruises coordinate all the different activities on the ship and make sure that we reach our objectives during the campaign, the scientific objectives. So we have a lot of people working on the ship doing all kinds of different activities. It requires help from the crew, and everything has to be very well organized, coordinated, so that we use the time we have on the ship as fully as possible.
Understand. And you, Peter, you've been on the Amundsen before, right?
That's correct.
Yeah. Do you have the same research objectives? What are your plans for this year?
Well, one always hopes that the research objectives evolve somewhat from one time to the next so we can make new discoveries. And so this time our research is focused more on the interactions between... So last time we were focused on air-sea interactions and the formation of ice, and this time we're focused more on the interactions between existing sea ice, older multi-year ice that we expect to find in the Lincoln Sea, and how that interacts with the ocean and the atmosphere.
Okay. And what about you, Jens? What is your role on board this cruise?
Yeah, so we have a mooring program as a part of the U Manitoba Canada Excellence Research Chair program. So those moorings we deployed last year, and our goal here was to recover these 3 moorings, which we have taken up 1 so far, and we have 2 remaining, and 1 is lost. And then I was invited by Marcel to help out with the sea ice research work on the ice floes.
Oh, interesting.
You know, so I'm doing that and looking at the temperature and salinity and the structure of the sea ice.
All right. So the 3 of you work on different aspects of sea ice, yet the exact nature of what sea ice is may not be very clear for everyone. I think the most important characteristic of sea ice is that it is formed from seawater, so salty water. Would you agree with this, or do you have other definition for sea ice?
So sea ice is basically frozen water that forms and melts and evolves on the seawater in the ocean environment. So you can have sea ice formed from refrozen snow or fresh water or something like that on the ocean, but it's still kind of classified as sea ice.
Okay.
But true, most of it is from salty seawater.
So if you have snow that melts on something that it is already on the ocean water and it refroze it's still sea ice.
Yes, because it's on the ocean, yeah.
Okay. Interesting. So I think it is quite useful that we go through a few icebreaking questions to see if we really know what sea ice is and try to understand what it is. So I have a first question for you. How does sea ice form? At which temperature, and how long does it take before we have actual sea ice?
Well, for sea ice to form, the temperature of the water has to first get cold enough. So you have to cool down the ocean sufficiently, that layer. Then that's when you typically starts forming fracil or some small little crystals, or meltwater comes out and starts forming. So that's the first. And then any growth of sea ice is then a function of that loss of heat from the surface. You need a cold atmosphere as well. So that's when you start, when the energy balance becomes negative in the fall, then the ice starts eventually form once the heat is lost from the ocean.
And at which temperature can sea ice start to form? I think we all know the answer. So Marcel, go for it.
So depending on the salinity of seawater, but at usual salinity, it freezes at around minus 1.7, minus 1.8 degrees. So
Okay.
lower temperature than fresh water.
What's the difference between an iceberg and sea ice?
Okay, well, so an iceberg is basically ice that's formed on land. So snow falls on the land, creates a glacier, and then the glacier eventually, over thousands of years, flows into the ocean, and it floats and chunks break off, and those are icebergs. And so this is ice that, contrary to the definition given by Jens a few minutes ago, did not form on the ocean.
Okay, so it's really the formation location. Interesting. And what can we find in sea ice? Can life persist in it? Maybe that's for Marcel.
Yeah, we can find all kinds of things because when sea ice forms, because it contains salt, the water will freeze, get solid, and reject most of the salts, most of the molecules that are large enough, which will concentrate in small pockets in sea ice. So sea ice in the end is like a sponge, which is made of a matrix of nearly pure ice, and it contains a lot of these pockets with more salted water. It's salted enough so that it cannot freeze, and this is where we find different kinds of microorganisms. We find viruses, bacteria, archaea, microalgae, other unicellular organisms, but you may find some fungi as well. And if they are large enough, or at the bottom of sea ice, you can find small animals as well, like worms or some crustacean, or even some fish larvae will live close to sea ice as well, not in sea ice, but close to sea ice.
I have another question, and I think this one is maybe for Peter. Again, how does sea ice interact with the waves in the ocean?
So good question. We have this very simple picture of how ice forms in the ocean, right? Like you have the air cools the water, you form crystals of ice on the surface, and they join each other together, and you get this like flat, thin surface of ice, like on a pond on a cold winter day. But then if you have waves and wind and turbulence, this mixes those crystals that form on the surface down into the water column, and you can continue to cool the surface. So when ice is forming, this can produce much more ice and allows much more air-sea heat exchange to cool the upper ocean further. So you can ultimately produce more ice. At the same time, waves also have some other interesting effects. For example, many people who have been on the Amundsen will have noted that when there are big waves, the waves break up the ice. And so then the ice is surrounded by water on more sides. It changes the albedo, and you can melt ice faster. And these are just two examples of many. Waves also affect the mixing in the upper ocean, which affects the heat content, which affects how quickly ice forms and things like this. And we can...
So, what is your favorite type of sea ice?
I think I like land-fast ice. Get stuck to the shore. You can work on it easy. You can go back to land and do your analysis and and it's interesting coastal processes occurring underneath with river flow, and it's used by people to travel, and there's lots of variations. So I like that part.
Practical and also very interesting. Okay. What about you, Peter?
Well, I'm a kind of a sucker for pancake ice, I guess. These are ice flows that get broken up by waves, either broken up or form in these pancake shapes. So they're little round ice flows that bounce into each other, and they have ridges around the edges. And they're big. If they're big enough, you can walk on them. And they look great, and they mean that there are waves and complicated offshore processes happening.
That's good. Yeah, I think these are my favorites too. What about you, Marcel?
Well, I like landfast ice too, and pancake ice too. But I like also what we've looked at a lot during that campaign. Multi-year ice is very surprising. Can be very, very thick. Can reach several meters of thickness. We call it multi-year because it survives few melt seasons. Can be up to 5, 6, or even 7 years old. It gets very thick, both because it has grown more, but also because it's very much deformed. Over its life, it has experienced phases of ridging, for instance, and when you core it, as we did during this campaign, there's a lot of surprises, and it's a complex cake.
For sure. Maybe one last question. During your field work, did you ever slip on sea ice? Is it slippery enough for that? All of you.
Me first? No, I never slipped on sea ice, because sea ice is not slippery at all. It's actually very rough surface typically. But I've slipped on other kinds of ice, like lake ice and things like that. So that can be pretty dangerous. I slipped a lot on the ice hockey rinks.
Yeah, that's certain. So it's not the kind of texture on which we slip typically.
But we can have melt ponds, and in this leg here we had refrozen melt ponds, and that's almost like freshwater ice, and it had a little bit of snow on top, so that was quite slippery.
Okay. Now that we all understand a bit more what sea ice is, let's get deeper in your respective field of research and expertise. Starting with Jens, what are your specific research interests as a physical oceanographer? But I think you have a strong interest in sea ice as well, right?
Yes, most of my research is linked to sea ice. I'm kind of interested in sea ice across the scales, from the smaller scales to the larger scale. It's interesting because sea ice properties are such, and there's so much of it that it really affects the climate system. So that's one of the interests. And then in the local, smaller scale, it's important for local processes, such as and for the animals that live there and the plants. And then as a material in the smaller scale, it's also super interesting material with changing with temperature and salinity and conditions and everything. So it's just kind of a very interesting material to study across all these scales.
And so to study all these scales, I guess you need many different approaches. So you probably use satellite imagery and field observations, all of that?
Yeah, you kind of pick the tools that help answer the question, like, is it about how much sea ice is drifting away from the Arctic or around the Arctic, or is it more about what happens underneath the ice and affects the properties of the ice as it forms? Or so then you have to study it in different ways. So I like studying with moorings and field observations, and that's more like a local scale studies of, you can see how the thickness evolves and how the ice is affecting the ocean, because as ice forms, it pushes the salts out, and the upper layer gets more salty, and that changes the balance, the stability of the water column. But on the other hand, also that when the ice melts, then it preconditions the next year and creates stratification. So it really changes the whole environment. So it's really kind of cool interaction between the ocean and the ice. That's what I'm kind of into at the moment.
Okay, thank you. And Marcel, I understand that you are working mostly on the optics of sea ice. Can you tell us more about that?
Yep, 2 things. I look at light in the sea ice, and I look at how this light is used by photosynthetic organisms. So really, I always work on those two different topics, which are very closely related. So I'm interested in figuring out to what extent light can penetrate and go through sea ice, through snow. First, there's very often snow on top of sea ice, which intercepts a lot the light mostly by reflecting it. Then it can be scattered and or dispersed or absorbed in the sea ice before a few photons may reach the bottom of sea ice, where it can support photosynthesis by microalgae that either live in sea ice or live at the top of the ocean. So I'm really interested at determining how light propagation through sea ice changes from fall when it forms to spring when it melts, and during all phases of sea ice growth and decay, and during all phases also of the presence of microorganisms in sea ice. So how they come into sea ice, how they survive during the polar night when it's very cold, there's no light, and then when they wake up in the spring, and possibly they bloom during spring and produce a lot of biomass.
So you talked about sea ice in the fall and in the spring. What's different? I assume that it's thicker because it had winter to grow. But do you have very different properties for these two types of sea ice?
Yeah. So first, when it forms, it's thin.
Mm.
It forms at fall. There's not necessarily a lot of light, so it's very much the phase during which microbes will colonize sea ice. We know that that during that phase they concentrate a lot in sea ice, and we don't know exactly how they do concentrate and why they get so numerous in sea ice during that phase. So it's the time when they mostly get there.
Okay.
During that time, there's not much light still available, but then they just mostly live there, survive. Some of organisms may have other activities than photosynthesis, may eat other organisms, for instance.
Okay.
And then when the sun comes back during spring, they start to photosynthesize again and to divide and proliferate during spring. And at that time, ice is much thicker. There's snow in general. So at some point, what may be limiting is not the sun elevation, but it becomes just the sea ice optical properties, which intercept a lot of photons to a large extent just by reflecting them. And then at some point, the snow will change because it will become wet, more transparent. It will melt. There may be melt bonds developing on top of sea ice, which kind of open windows on sea ice and allows light to penetrate more. And that will trigger more biomass production in sea ice, but very much in the water column afterward.
Okay. Do you have anything else to add to your research focus? Or?
Well, yeah. So my activities are based to a large extent on fieldwork, the kind of fieldwork we are conducting now, but it's also based on laboratory experiments. We do isolate some representative organisms that we then grow in the laboratory, and then that we put under conditions that they may experience in the natural environment. It's easier to look at them in the laboratory. We can make much more measurements, more accurate measurements, and working on single species make things easier also to understand more basic processes. The other tools I used is, one tool I use a lot is remote sensing. So looking at the ocean from space, first optical remote sensing. So I look at light again, but light from space when looking at the frozen ocean, and light as a tool to measure things.
Thank you. And Peter, your research interest is oriented towards ice-ocean interactions, that I understood.
So I spend a lot of my time working in the marginal ice zone, which is the area of sea ice, typically around the border of the sea ice, which is influenced by oceanic processes, like processes you find in the open ocean. And the reason why I'm interested in this is because we're seeing massive changes in the marginal ice zone in the world right now, actually at both poles. So in the Arctic, we've seen this decrease in sea ice extent, something like 40% since the beginning of the satellite area, which is quite large. And it means that we have these new seasonal seas that open up in the Beaufort and Chukchi Sea regions each summer. And in the Antarctic, the situation has also been quite interesting because up until 2016, 2017, the Antarctic sea ice was expanding. And then all of a sudden there was a massive decrease in sea ice, which some people have been calling a regime shift, where now we see summer sea ice extents almost like in the 30 to 40% range, less than that 1970 to 2016 median. And so what this means is that the sea ice is expanding and contracting more than it used to at both poles. And so that means that the processes of expanding around the boundary are becoming more critical to understand. And it seems that we don't fully understand them that well yet. The change in the Arctic is particularly interesting because there used to be no open ocean processes at all. And now you have things like wind and wave-driven mixing in the upper ocean, which affects heat transfer, heat content, and how ice forms. So there was some talk previously in this podcast about wave effects. That's just one example, but there are many others. And so one thing which I have noticed is quite critical about these marginal ice zone processes is that they're very spatially heterogeneous, which means they vary massively over relatively small scales. And so that's something that is very important, but it's difficult to capture with measurement systems. And so that's kind of one of the things that I've been focusing on in this cruise and others is developing measurement systems where we can capture that spatial variability and understand these physical processes.
So something that happens in one area may not be happening like 100 meters away. Is that correct?
Exactly, that's correct. So you can have patches of open water or floating flows that change massively the exchange of heat and momentum between the atmosphere and the ocean by like orders of magnitude. And you can't just average them over the whole area and assign one value. Like they do not add up in a linear way. And so this is why we have to kind of capture this intermittency.
So you talk about how a marginal ice zone is going to be more and more present. So how is that transferred into the research that you all do here? Do you also have new research interests because of this ice melting? Or is this something that you take into account into your research?
Yeah, sure. It's an important motivation. It's not the only one. We are both interested in just learning more on how it works, but also in how it may respond to current changes. So the first very obvious change has been mentioned already. There is less and less sea ice in the Arctic. Sea ice could be considered as a blanket on top of the ocean. And if there's less sea ice, more of the ocean is exposed to solar radiation. So one may think that if there's more light, there may be more biomass production in the ocean. At the same time, if there's less sea ice, what about the organisms that do live in sea ice? Well, what we know now is that in fact, most of these organisms can live both in sea ice and the ocean, so that's okay. But we did document in the past decade a significant increase in biomass production in the Arctic Ocean as a consequence of the decrease in the extent of sea ice during summer. Right, during winter, the extent of sea ice in the Arctic is not that different. Mm-hmm. It's very different in the summer, when it melts much more in the summer than it used to.
Do you have anything to add, Jens?
Oh yeah, when we have more open water forming nowadays, then there's of course much more solar radiation being absorbed in the surface of the ocean. So then the ice, as a consequence, is not growing as thick as it used to do. So that has impacts on the multi-year ice. What we've seen on, for instance, in this cruise is likely that the ice that we have is not that old. So the thickening process is likely way more affected than before by dynamic processes. So I'm thinking that the survival of multi-ice will be a lot to do with how dynamic the ice is. So how much waves and how much wind is affecting it. Some places also tidal interactions. And that impact of thickening the ice is probably increasingly important.
Yeah, about that, we had a lot of field work during this cruise. And I know, Jens, you were coring quite a lot. And you had, for example, a core that was relatively short next to a core that was very long. So you had a lot of differences in the ice thickness. Is that correct?
Yes, just in one site, because we have these melt ponds and refrozen melt ponds. So you can drill through a site, a hummocky site, where you can have 4 meters of ice. I think we had 4 meters and 30 centimeters in one place that we took a sample of. Maybe that's longer. And then next to it, very deteriorated site, where you have only 50 centimeters of really deteriorated ice.
And so during these operations where you go in the ice and you do ice coring, as you just said, what are you trying to find? What can you tell from these cores?
Yeah, so we're measuring what I'm measuring here with Bastian and Matthew as well. We are just measuring the temperature and salinity, and we're looking at the texture of the ice to have some kind of idea of how the ice was formed, what kind of ice it is. It can be granular, columnar, or there's some sort of metamorphic refrozen version of the ice. And we're seeing that latter one quite a lot here. Actually, it's really melted and refrozen. And this is then, I don't know if you can really say much about how old the ice is from this, because it's so mixed up, but at least it can help support other people's observations when they're looking at bacteria or phytoplankton or algae or whatever they're looking at in the ice. Isotopes.
Yeah, because we had many people coming on the ice and collecting cores. I know they were using it for trace metal analysis, and we actually had people during another podcast studying the contaminants, and they were also taking cores.
Yeah.
And what about you, Marcel? I know you have also ice coring operations or operations taking place on the ice. What are these for? What are you doing with that?
So I will extend a little bit on what Jens explained. He was measuring temperature and salinity, and it does give us some very important information to understand light propagation in sea ice, but also the possible presence of life. Why? If you think about freshwater ice, in freshwater ice, there's not much space for microbes to live. There's no pockets, of liquid water that is very salty. It's like glass. And at the other opposite, when you have ice forming from very salted water, you get these small pockets of liquid water where you find microbes. And in between, there's all possibilities. So when sea ice, so formed from seawater, is not so cold, you get more of these pockets that are larger with less salty water. As you cool down the sea ice more and more, these pockets will become much smaller, more salty. The volume that will be inhabitable in sea ice will become smaller. So this is why this kind of information is important for people who look at microbes living in sea ice. The other things we look at in sea ice is so I am interested in microalgae, so we measure the amount of pigments in sea ice as an index of their presence. We will collect some ice samples that we will then melt, try to look at them under the microscope. If there are microalgae, the species that are present, then you may want to measure a number of physiological rates or processes like photosynthesis, for instance, the rate of carbon fixation or of oxygen production.
Thank you. Peter, what have you been doing on the field during this cruise? I haven't seen you on the ice, but I think you we're deploying quite a lot of instruments.
Yeah, so we haven't been sampling ice directly. That sounds like a lot of work. So what we're doing is we're measuring what the ocean does around the ice. So, our interest in these ice flows is not so much their contents and their interior structure, but rather their exterior shape, size, and what it does to the ocean. So, for example, you have a boundary between ice and the ocean. This changes how much wind is pushing on the ocean because, as Marcel said, the ice acts like a blanket. So you have an ice flow and it kind of isolates the ocean from the atmosphere. You take that away, or you have a space in between, and then all of a sudden the wind can push on the ocean. And so we're interested in the turbulent structure between the ice flows. And there are many reasons for that. So first of all, of course, we're just interested in, how the atmosphere changes the ocean. So whether it cools it, heats it up, what this does for ice formation and so on, but also the turbulence that is driven by this exchange does things like deepen or shallow the mixed layer, which can access things like nutrients and so on deeper in the mixed layer. So this is kind of a nice relationship, or a relation between our work and some of the other people on board here. And so to do that, we have a couple of autonomous vehicles. I guess the one that most people have seen on this cruise is a autonomous catamaran, which and you might ask why we need to use a catamaran to measure these things rather than just using the ship, which is also right there. And the reason is twofold. One is that the ship is very large and it stirs the ocean quite a bit down fairly deep, and so to depths at which the processes that we're measuring start to matter. And so we can't just measure turbulence or salinity and temperature right from the ship. So we have to get away from the ship, and so we use this catamaran.
Yeah, just like at the moment we're hearing the engine, I believe this next to your measurements would probably mess things up.
Exactly, yeah. And so there's that aspect, but there's also the aspect that we want to explore the spatial variability. Like, how does the exchange between the atmosphere and the ocean change right next to a flow compared to farther away from the flow, or in the middle of a lead or something like this? And so we use this little autonomous vehicle to map that sort of thing. And so that's what we've been doing.
Okay. And well, I think that concludes our episode. We've been talking about what you are studying, how you're studying it. Do you guys have anything else that you would like to add?
Yeah, I guess I would add that the goal of this campaign was to look at the so-called last ice area, to characterize it and observe how it evolves as it passes from the northern end of Nares Strait to the southern end of Nares Strait. And so we managed to do many of those goals. And I think the real value of this campaign is not necessarily in each individual measurement, but rather how they will interact. And so what our measurements will give to other people, and what other people's measurements what value they will add to our own. And I think this is something that's a little bit unique about this campaign, and it promises to be very valuable from that point of view.
Yeah, so you think you will get a better understanding of the global picture of this sea ice that you were observing, or just the environment that we're in?
Yeah, exactly.
These were good concluding remarks. Thank you, Peter. Well, thank you very much for joining us today. I hope you had fun, because I had fun and I learned quite a lot of things. Thank you very much for your presence.
Thank you.
Thank you very much.
Thank you.